Okay. All right, we are now recording, and I will go back to my slides.
Yep, there you go.
So, I'm James Rhoads. I'm the NASA project scientist for ULTRASAT, and today we have a program that will begin with a short introduction to the US role in the ULTRASAT mission, which I will do. Then Eli Waxman will present from the Weizmann Institute for Science in Israel and tell us about the mission overview. He's the PI. After that, Yossi Shvartzvald, who is the project scientist in Israel, will give us a summary of the mission's technical capabilities. Vandana Desai from IPAC will tell us about the US archive. Bob Blum will tell us about the LSST Rubin partnership with ULTRASAT. Valerie Connaughton from NASA headquarters will tell us about the open proposal call for participating scientists, which is timed somewhat to match this meeting, so that's open and you'll hear more about it. And then Avisay Gal-Yam will tell us about how ULTRASAT fits into the time domain multi-messenger ecosystem. Then we have a series of science shorts by half a dozen of our researchers, and then we'll move to an open Q&A session. Time permitting within this schedule, we might be able to fit in a couple of questions after presentations, especially if speakers run short. I'm off to a flying start on that with my 6 minutes of technical difficulties. But at the end, we have half an hour for open discussion, questions and answers, and during that time, I'd like some of the speakers to come up to the front so we can do it sort of panel style. So ULTRASAT in a nutshell, it's the ultraviolet transient astronomy satellite. It's a single band wide field near UV imaging mission with a 230 to 290 nanometer passband. It has a 200 square degree field of view and about a 33 centimeter aperture. And in the focal plane, there's high quantum efficiency CMOS detectors, 5 arcsecond pixels. The PSF ranges from about 5 to a bit over 10 arcseconds, depending on position in the field of view. Yossi's talk will have all of that. There's a 3-year prime mission life at geostationary orbit. It has basically a 24/7 duty cycle of observations, which is split between survey mode and target of opportunity. And it'll do an all-sky survey in the first 6 months, and then after that is basically a time domain mission, and it reaches 22 AB magnitude and a bit in 300-second exposures. ULTRASAT is an Israeli mission with US and German participation. The Weizmann Institute in Israel is the lead science institution. Israel Space Agency is also an equal partner on that side with the construction of the mission. The camera is being built by Desai in Germany, and the telescope and spacecraft by aerospace contractors in Israel. NASA's roles in this mission are to launch ULTRASAT, select and fund participating scientists who will join the science working groups and will have data access during the proprietary period, and to provide a US science-based archive and participate in the alerts. ULTRASAT also has a separate agreement with the LSST Rubin project, which Bob will tell you about in his talk. ULTRASAT and NASA science goals are well aligned. The 2020 Decadal Survey identified 3 broad scientific themes for the decade coming: worlds and suns in context, new messengers and new physics, which includes time domain and multi-messenger astrophysics, and cosmic ecosystems, which includes star formation and galaxies and galaxy formation. As you'll see, there's ULTRASAT contributions to all of these areas anticipated and covered in the working group structure. I also wanted to mention NASA has its core values of safety, integrity, teamwork, and excellence and inclusion, and we expect to strive for all of these in the NASA participation in this project through our partnerships. The international agreement that all of this runs under is a partnership that's negotiated at State Department level, and it's called an implementing arrangement. The document is in, I think, essentially final form and is working its way through, I think, final signatures in the coming month or two with any luck. The process is a little bit opaque to me, but I understand that it is quite near conclusion, and it's part of a broader sort of framework agreement between the US and Israel for peaceful scientific use of space and the near space environment. I wanted to briefly show you what the US org chart for this looks like. So Mark Clampin and Sandra Kaufman are the Astrophysics Division leadership at NASA headquarters. Shahid Habib is our program executive, and Valerie Connaughton, who's here in the room, is our program scientist. Her deputy is Sanaz Vahidinia. Jennifer Mason for the international office at NASA has been involved in getting that implementing arrangement through all the hoops it needs to go through. And then at the NASA Goddard side, Goddard is the lead science center for ULTRASAT and also the lead sort of project management for ULTRASAT on the NASA side. So Barb Grofik here is our program manager. Kathy Barclay is her deputy, is also at the AAS. Mark Matsumura, who's here, is our systems engineer. And then we have at Kennedy Space Center, Sean Daly, Eran Fournier, and Malcolm Boston working on, the nuts and bolts, both figuratively and literally, of getting this thing launched. And we have 3 other engineering support people working with Mark. The project leadership in Israel is Eli Waxman, who you'll hear from. Avisay Gal-Yam is the deputy PI. You'll hear from him as well. The program manager, Udi Netzer, is not here. Yossi Shvartzvald, Eran, Ofek, Sagi Ben-Ami are all speaking in this session. And I'd better move along because I'm a little behind. So, launching ULTRASAT, NASA will arrange the launch of ULTRASAT to a geostationary transfer orbit, and we're exploring commercial rideshare options for that launch, certified by the FAA. Kennedy Space Center is the lead NASA center for the launch, and ULTRASAT is going to go from the transfer orbit to its final geostationary orbit somewhere over West Africa under its own power. Our second contribution is science working group participation, and there is a proposal call open now, Roses Element D19 of 2022 Roses. There's a due date of March 31, so this is active and live, and you'll hear more about it in Valerie's talk. The Science Archive is going to be hosted at IPAC. It will be a complete archive of ULTRASAT data, and there will also be tools that they're developing to enable the US community to make more effective scientific use of those data. And Vandana will tell us more about that. NASA also anticipates participating in the ULTRASAT alert definitions via the Transients Working Group of the ULTRASAT project. Wanted to mention that Goddard is actively upgrading the GCN architecture to be effective in the upcoming era of many, many more alerts than the GCN initially had to handle. And there's a natural synergy between that and the ULTRASAT project. I also wanted to briefly say what I do. So my role as the project scientist is to coordinate scientific interaction between the NASA community and the ULTRASAT project and community. I attend the ULTRASAT Science Board meetings and some other project meetings. I'm supporting and coordinating the participating scientist program as it gets underway. And also I'm liaison to the archive effort, and there's outreach efforts which we haven't really gotten rolling yet, but expect to do in the nearish future. I also liaise with Bob and the Rubin Observatory, and the overarching goal of all of it is to maximize the science. So the Rubin Observatory partnership, I'll let Bob speak to that mostly, but there's clear science value in combining the ultraviolet with the optical from Rubin, and Bob will speak to that. So finally, I wanted to just show you what the ULTRASAT working group structure looks like. And this maps the ULTRASAT working groups to the NASA program analysis groups. So there's the Cosmic Origins Program Office, the Physics of the Cosmos Program Office, and the Exoplanet Exploration Program Office. These are a way that NASA divides up its science into thematic areas. And these are the working groups that exist under the ULTRASAT project science board, and we've got a rough mapping here. So cosmology, galaxies, active galactic nuclei, transient stellar explosions, gravitational wave sources, tidal disruption events, and gamma ray bursts. And then exoplanets and the star-planet connection, stars, stellar structure and evolution, and solar system. And then there's also a set of working groups that I think apply to all of the NASA focus areas equally: data analysis, transient alerts, and follow-up. So closing thoughts for my presentation. Think about what Science Ultrasat can enable for you. The Participating Scientist program call is open, so this is a great time to do that. For context, I've put up here links to the 2 science workshops that the project has held at the Weizmann Institute, and I've put my email for later questions. And I think it's time for me to hand off to Ellie.
Thank you, James.
Yes.
Let us just share our presentation here.
Yes, that would be good. Let's see if I need to click a button to stop sharing.
Yeah.
I think if you share, it may take over automatically.
Okay. Yes. Okay.
Okay, so I have full screened you. Now, if you full screen yourself, that will...
Does it show okay on your side?
It shows up. I just need to move a couple buttons and make it... There we are. So now we have your slides and you and nothing else on the screen. So take it away, Ellie. Thank you.
Okay. Thank you, James. So I'm Eli Waxman. I'm the ULTRASAT PI, and I'm happy to present the mission in this session. One of the main goals of which is to encourage US scientist participation in our working groups. As James mentioned, the ULTRASAT is a mini satellite that will carry a wide field of view ultraviolet space telescope that would greatly enhance our ability to study transient events. The mission, as mentioned, is led here at Weizmann with the support of the Israel Space Agency and the participation of NASA and our German colleagues at Desai. I will briefly present the mission and the main goals of it, and then Yossi will describe in more detail the technical capabilities. So the main unique properties of ULTRASAT are its very wide field of view, about 200 square degrees, and its high UV sensitivity reaching 22.5 magnitudes for 900-second exposure. The combination of this field of view and sensitivity provide ULTRASAT with access to a very large volume of the universe in which it can detect transients. You can see in the plot the instantaneous volume accessible to different surveys, and you see that, and it's normalized such that ULTRASAT is 10 in these units. You can see that ULTRASAT will detect transient at a rate which is about 300 times larger than what Galax was capable of doing, 10 to 100 times better than any current optical survey, and comparable to the reach of the Rubin observatory that is being constructed. Now, in addition to the very large volume that would be accessible to ULTRASAT, it would also open a new window in wavelengths, observing in the near UV, and also in cadence, providing continuous months-long light curves with minutes cadence. In addition, being in space, in a geostationary orbit, it will provide real-time alerts for the detection of transient events. And it would also have a very strong TOO capability. It would be able to slew within minutes to any point on the sky and follow up transients detected by other facilities. The key science goals of ULTRASAT are the detection of electromagnetic counterparts to gravitational wave sources and the study of supernovae. Starting early or mid-2026, we expect gravitational wave networks, detector networks, to provide about 10 Newton star binary merger events per year with an error box of about 100 square degrees. And ULTRASAT will be able to localize UV emission from these sources very quickly. It would reach any point on the sky in a matter of minutes, and it would cover the entire error boxes of the gravitational wave sources in a single image. So it would provide rapid detection and also detailed UV light curve of the sources lasting for days to weeks. For supernova explosions, ULTRASAT will detect early our timescale UV emission from hundreds of supernovae per year. And this would enable us to measure the properties of supernova progenitors and also to constrain the mass loss history of these progenitors prior to the explosion. The fact that we will detect hundreds of supernovae per year is important because it would enable us also to detect the rarer supernova explosion from blue supergiant and Wolf-Rayet progenitors. And this is important because it will enable us to map the progenitors to the different progenitor types, to different supernova types for a wide range of supernova explosions. And you can see in this histogram how strong ULTRASAT will be in this game. You can compare the number of supernovae that will be detected within 1 day and 1 hour by ULTRASAT compared to other surveys like Rubin and ZTF. The first and so far only detection of electromagnetic emission following a neutron star merger detected by gravitational wave detectors provide very strong support to the ULTRASAT mission. So as you know, the electromagnetic counterpart to this source was detected only half a day after the gravitational wave detection. And this is due to the fact that the counterpart was searched for by narrow field instruments going galaxy by galaxy within the error box of the gravitational wave detection. This exercise is going to be very difficult to carry out when the horizon of the detection extends to 300 megaparsecs. There will be thousands of galaxies in the error box, and ULTRASAT, on the other hand, will cover the entire error box in a single image, so it would be able to detect the emission very quickly. This event, although it was detected rather late, it was very bright in the UV, and ULTRASAT will be able to detect such sources to 300 megaparsecs and more. And also we've learned from this event that constraining the composition of the ejecta and which elements were produced in this merger is challenging, and early UV emission would be crucial for differentiating between different models. In addition to these two top science goals, the ULTRASAT will have a major impact on a wide range of transient astronomical transients that are interesting for us to study. This is a table showing some of them. We will not go, of course, through this table, but as James mentioned, we have working groups focusing on different types of objects as part of the ULTRASAT mission. I would mention just one additional example to show that ULTRASAT capabilities are not limited to the high energy end of the astrophysical transients, and show that ULTRASAT will also be relevant for planet habitability studies. So you know that planets are being searched around M-Dwarf for young solar analogs, and these stars are active in the UV, and the UV activity can both limit habitability and also affect biomarkers like ozone in the atmospheres of those planets. Now, the UV activity of these dwarfs is not well mapped, and ULTRASAT will resolve this issue. It would monitor several 100,000 of these dwarfs and would provide a detailed account of the UV flaring activity from minutes to months scales across different ranges of flare luminosities. Okay. A word about the mission and its structure. So at the center of the satellite sits the telescope, which is being constructed by ELOP, an Israeli company, according to our design. At the center of the telescope sits the focal plane array, the UV sensitive camera. The sensors have already been produced by Tower, which is another Israeli company, and the integration and remote electronics are actually currently being constructed by our Desai partners. And the telescope will be integrated into the satellite by the Israeli aerospace industries. As James mentioned, the satellite would be launched by NASA to GTO orbit, and we expect this launch at early 2026. We would carry fuel for a 6 years mission. Reliability requirements are for 3.5 years, but normally Israeli satellites live longer, so we expect a 6-year mission. The key technological challenges that we had to face were related, one, to the high quantum efficiency that we require in the UV band. And what you see on the left plot are measured UV quantum efficiencies for different types of coatings that we have tried. And we have chosen this T2 right-handmost coating that provides overall more than 60% quantum efficiency average in this band. The second challenge was to produce good PSF across the very wide field of view of ultrasat. What you see on the right-hand side is, of course, a model calculation. The telescope is not built yet, but we achieved this 5 to 8 arcsecond PSF across most of the field of view as required. This is just to show you that construction is ongoing. On the left side, you see this is one of the tiles, one of the 4 tiles that would serve as the focal plane array, which is being tested at Desai. On the right-hand side, you see the polishing of the mirror ongoing now at ELOP. Overall, the mission program is on track. All the teams in the industries are engaged and working. We believe that we have identified and are managing all the major risks, and we believe that we would be able to reach our launch goal early 2026 with a total relatively modest overall cost of the mission, including launch, of about $110 million. A word about the science collaboration. Alerts, of course, would be provided to the community in real time. All the rest of the data would be proprietary for about 12 months. Members of ULTRASAT working groups would get immediate access to all the data. And we have 13 science working groups, as was already mentioned. They are open to all Israeli astronomers, and most of the Israeli astronomers are already members of these working groups. NASA, in return for its launch contribution, would receive 8 US PIs that will be able to join the working groups. Desai would receive 3 PIs in return for the camera contribution. And as James already mentioned, we have concluded the negotiations with Rubin, and they will receive 6 US PIs for their contribution to the mission. And the NASA call is already out, and I encourage everyone who are interested to submit proposals to join ULTRASAT. Last slide, just a summary of the science impact of ULTRASAT. With a discovery volume 300 times larger than GALEX and the continuous minutes to months cadence and high UV sensitivity and real-time alerts to the ground, I think ULTRASAT will revolutionize the study of hot transient events. It would have a broad impact on a wide range of science topics. I've mentioned gravitational waves and supernova explosions, but it would also be important for the study of tidal disruption events, AGNs, and other topics that would be also mentioned partly later in the session. And finally, we will do all this groundbreaking science at a relatively an affordable cost of a satellite mission. Thank you.
Okay. Maybe what we can do is go ahead and have Yossi speak, and then we're going to have just a slight break in the program because we have an extra hello from NASA to insert, which we'll come to in just about 10-15 minutes after Yossi's talk. Okay? Take it away.
Okay. Can you see my screen now? James, do you see the screen?
Yes, we see it. Can you?
Okay, great, thanks. So hi, I'm Yossi. I'm the ULTRASAT project scientist. I will go over the performance and capabilities of ULTRASAT. The presentation will have a lot of information. I probably won't have time to go over all the details. I just encourage everyone that is interested to go to the ULTRASAT website. And also this presentation will be available. And at the end, you can always send us emails and ask questions. We are very happy to give all the details that are needed. So I'll continue from the implementation slide that Ellie presented, and I'll just go into part by part of the components of ULTRASAT and tell you about the capabilities and the current understanding that we have on them. So first, we'll start with the camera. As I said, this is the contribution of Desai. The ULTRASAT focal plane array is composed of 4 BSI CMOS sensors, which together cover an area of 14 by 14 degrees, or a total 200 square degrees, with pixel scales of about 5.5 arc second. The camera is cooled to 200 Kelvin in order to minimize the dark current. And in a minute, I'll show you the plot that Ellie showed about the high UV quantum efficiency. I'll just say that this is a new design, a custom design sensor. All the sensors already been produced and passed full verification of the performance. The flight sensors have been diced and are now being packaged, and we're going to select the best one of them in order to take into the flight camera. So as we said, the most challenging aspect from the camera perspective was to achieve the high quantum efficiency of more than 60% within the operational band of 230 to 290 nanometers. And we tested the 3 different AR coatings, and eventually all of them, by the way, passed the 60%, but in order to optimize with the other optical throughput, we chose the coating T2. And what you can see on the right, that also we are starting the production phase of the camera. So we have tiles being produced and tested, and also the camera structure and electronics are now being produced and integrated. So the telescope is a modified Schmidt design with a 33 centimeter clear aperture. It has at the entrance a pair of lenses, a fused silica and calcium fluoride. Then the light goes through a 50 centimeter mirror back to another pair of flat field lenses of fused silica and calcium fluoride. And then just in front of the focal plane array, we have a sapphire filter that is important to suppress the out-of-band wavelengths. Also from the telescope aspect, we are already in the production phase, and most of the optical elements have been produced or are being produced, and we're expecting around the end of this year to start the actual integration of the telescope. Now, in front of the optical tube, we have a baffle, slanted baffle. The baffle have 2 main purposes. The first of which is the common one, which is stray light. So we either prevent or significantly suppress the light from the sun, Earth, and Moon. And this sets our pointing limits that you can see in the table on the right. And the key issue, or the key thing that was optimized in our design, is to enable at least 50% of the sky at any given moment, even in the worst case where all three objects are not overlapping each other. Now, the second role of the baffle is actually to suppress the flux of trapped electrons that are in a geostationary orbit. And when these electrons hit the front lens, they produce Cherenkov radiation, which is one of our dominant background noise. And actually, without this baffle, it was the dominant background noise source. And in addition, by reducing their flux, we'd also reduce the transmission degradation of this lens. So combining the camera and the optical performance, we can build the total throughput of the system. So you can see on the left plot, we reach about 25% in-band throughput, while in the out-band, in the red part, or the visible wavelengths, we have 10 to the minus 5 suppression, which is very important, obviously, in order to suppress the red leak. What you can already see here, or it's in this gray shades, that we have radial dependent performance. In terms of total throughput, it's not really a big difference. Is due to obscuration and different angle of incident in distribution on the detector. But as you will see in this next slide, for other parts, it's actually very, very important. And we can derive color-color relations that are important to understand our limiting magnitudes compared to other bands. In terms of the optical design, it is optimized for the largest grasp. And for that, we actually don't have a uniform PSF, but again, a radial dependent and color dependent PSFs that you can see on the left. So on the y-axis, we have the radial distance, and on the x-axis, we have the wavelengths. And we see that actually the best image is at around 4 or 5 degrees off center. Now, when we take this color-dependent, radial-dependent PSF and calculate the effective PSF for different sources, we can see on the right the effective PSF that we'll have for different sources. So for blue sources, we are about 8.5 arcsecond mean PSF in the central 170 square degrees where the grasp was optimized. And for red sources, it is much worse. The PSF, and again, with the suppression, it actually allows us to eliminate the contamination of red sources. Now, the next step is to estimate our limiting magnitude. So this is for a nominal 300-second exposure and a coding of 3 images, which is what we set as our nominal visit. And you can see that we achieve throughout these 170 square degrees about 22.5 AB limiting magnitude for blue sources, and again for red sources this is significantly different. In the table on the right, you can see our background noise, and it is dominated by zodiacal light, and second by the Cherenkov radiation. And instrumental noise is only at a lower rate, and this is how we designed it, and actually also tested it and verified it on the dyes that were produced. We can also see that the sensitivity and the saturation limit, which is defined here by the solid circle at the end of each curve, is again also both radial dependent and source dependent. As for the spacecraft, so you can see on the top right the configuration and all the details of the different components. The launch will be to GTO orbit, and we have enough fuel. Actually, half of the mass of ULTRASAT is for the fuel required to do the self-propulsion from GTO to GEO orbit. But this GEO orbit is very important. It allows us to have continuous transmission to the ground, and both for command, of course, but also from the data. And this is for all possible positions. So anywhere that we're going to slew, no matter where we point, as long as it is not within the restriction pointings of the Earth, Moon, and Sun, we can get continuous data downlink. We are able to instantaneously slew to anywhere in the sky that is allowed within less than 15 minutes, and actually the typical slew time will be around 6 or 7 minutes. In terms of technical aspects, we don't have any limits on the number of TOOs, except that we can have only 25 TOOs per year with negative energy balance, and for a random distribution of transient, we expect it to be about 33% of the TOOs. For those hard TOOs with negative balance, we can last for at least 3 hours. This is the requirement, and of course for the others we can stay there as long as needed. This leads me to the modes of operation of ULTRASAT. So the main nominal mode of operation will be a survey mode. We're gonna have 2 survey modes. The first is a high cadence survey that we're gonna devote 21 hours a day for it, which is staring at one field with 5-minute exposure. So continuously with 5-minute exposures. In addition, we'll have a low cadence survey of 40 fields visited once per 4 days. And we're gonna devote the rest of the 3 hours per day to this low cadence survey. All data from the surveys will be downloaded and analyzed in real time, and within 15 minutes from the end of exposure, the Science Operations Center will distribute alerts on new transients. The survey fields will be switched every 6 months between North and Southern Hemisphere in order to minimize the zodiacal contribution. Every now and then, we're gonna interrupt the survey observation to target of the opportunity, which is directly related to our prime key goal of follow-up of gravitational wave events. And as I already said, we can instantaneously observe more than 50% of the sky in less than 15 minutes and for at least 3 hours with no real limitation, and continuous transmission to the ground, and of course also real-time analysis and alert distribution or localization, if you would like, out of these TOO. In the first 6 months, we're gonna build the UV all-sky map. We're not gonna devote the entire 6 months for this, but only 3 hours a day instead of the low cadence survey. So the high cadence survey will start immediately at the science observations, but it will take us 6 months to build this all-sky map. It will give the static sky map 7 times deeper than Galax, and it will also serve as the reference images for the TOOs that we're going to do later. In terms of operation, we have 2 centers. The first is the ground control station at the Israeli aerospace industry, which is responsible for direct communication to ULTRASAT. But here at the Weizmann Institute, we're building the Science Operations Center that will be responsible for all the scientific aspects, both observational planning, as well as the image and data processing, and later the distribution of the data products and alert generation. I'm gonna recap again what Eli said about the data policy. So all ULTRASAT alerts will be publicly available to the entire community, of course. The more detailed data products will be available only to the working group members or the collaboration, but they will be available to everyone 12 months after in a dedicated data release that we're gonna issue from our data center as well as from the NASA archive, and Vandana will talk about it in a few minutes. Yeah, that's it. So this is a recap and a summary of the performance of ULTRASAT. I won't go over them again, and you can ask a question at the end. I just want to emphasize two relevant dates. The first of which that we're going to have a collaboration-only workshop this summer in July. It is after the selection of the USPIs, and we are and we would be very happy that the USPI would participate in this workshop. It will be held here at the Weizmann Institute. And the second, that we still have an open call for ULTRASAT Prize Fellowship for 4 more days. So if we have young students or postdocs in the crowd, you are very encouraged to apply to this fellowship. And that's it.
Thanks, Yossi. So before we move on to the next scheduled presentation, I'm very pleased that Mark Clampin, who's the head of astrophysics at NASA headquarters, has been able to join us for a few minutes. I'd like to invite him up here to say a few words on behalf of NASA.
So good morning. I just wanted to take a few minutes to welcome our Israeli partners to this session and thank them for attending and talking about ULTRASAT. I actually recently had the opportunity to meet with the Israeli Space Agency and the ULTRASAT team at the Weizmann Institute in Tel Aviv and discuss this program. We had a very useful meeting. NASA was also very pleased to be invited to come and see the ULTRASAT facilities and also talk about the science. So I just wanted to emphasize that ULTRASAT really shows the value of international coordination when we talk about how we're going to achieve our Astro 2020 TDAM goals, meeting the recommendations that were made by the Decadal Survey. And as you probably have already heard during this session, in this case, the US is providing the launch for this satellite, and then we'll also be heavily involved in the science program as well. So this is a great opportunity. I also think, just to finish up, that it also shows the value of coordination of programs. One of the issues I highlighted the other day is how we coordinate all of these different international programs, and this is a great example of how certainly NASA's Astrophysics division is going to try to work on this issue with our international partners as we go forward. So once again, welcome to our Israeli partners, and look forward to hearing the rest of the talks this morning. Thank you.
Let me say, Mark, thank you for the support that NASA is providing for the mission and for the good cooperation and collaboration, both on the science side and also on the technical side. And I look forward to the joining of the US PIs to our team.
Thanks, Eli. So I think next up in our schedule is Vandana Desai, who is speaking to us about the archive. And let's see if, I'm just trying to see that the slides go up, Vandana. It says input B, but now it shows it. So I think I just bumped the cable. So I think you're all ready to go. Without further ado.
Okay, sorry, I was trying to figure out how to unmute myself. Let me do the slideshow again. All right, thank you. I'm very excited to be hearing about ULTRASAT. I'm going to be talking about the US ULTRASAT archive. I am the science lead for the URSA archive at IPAC at Caltech, and we are one of the NASA Astrophysics mission archives, and you can see that we have some experience. We hold data from many NASA archives, including Spitzer and in the time domain, WISE and NEOWISE, but also some non-NASA programs such as ZTF that are also in the time domain. So as was already mentioned in the previous talk, there are going to be 2 ULTRASAT archives. One will be at the Weizmann Institute of Science in Israel, which will provide ULTRASAT members with access to proprietary data. And they will also issue alerts to the entire astronomical community. The US archive will be hosted at URSA in the United States, and we will provide a permanent science archive containing the public ULTRASAT data, so not the proprietary data, but also the documentation and various services and tools that will be designed to meet the needs of the US research community. When we build the Ultrasat archive at URSA, we will be following the standards that we always follow for the other NASA astrophysics missions. And as for the content of the archive, we will hold all of the basic data products that will be identical with those that are available at Weissman. As we build our data access and exploration tools, we will be working with the Ultrasat project to ensure that that they will be complementary rather than duplicative. So as we talk about the public data releases, we will be serving images that will be at the various processing levels. So we'll have the raw processed images, the masks and the difference images, and we will also have catalogs of the time domain measurements. So the first public data release is planned for 18 months after the start of science operations. So that includes the time to take the first 6 months of data, which will be the content of that first data release, plus a proprietary period. So this first data release, representing the first 6 months of science operations, will be about 230 terabytes of imaging and 50 billion rows of catalog data. So just for context, the NEOWISE mission, which has been, we're on our 8th annual data release, is currently at 150 billion rows. It is the largest catalog that we hold at URSA. So you'll see that just after the second data release, which will encompass 1 full year of data in addition to the first 6 months of data, we're going to be on the same order as NEOWISE. So if any of you have used those data, it's a very rich, very large data set. And so we are really seeing we expect to see a lot of legacy value out of these data sets, the Ultrasat data. So when we design our tools, we will have data discovery tools as well as data access services, and they're going to be based on virtual observatory standards. So these are, international standards for accessing images and tables, and they're used by all of the NASA astrophysics archives. And this is really useful because it's going to allow people to use some of the big data tools that are available, say, in Python. So if you use AstroQuery or PyVO, you'll be able to access the Ultrasat data through those because of this standardization that we use. And then for the data exploration tools, we're going to be also offering, in addition to programmatic access, some GUI access. So we'll have a graphical user interface that will guide users through the data and allow them to explore the data with really big data sets like this. It's very important because you can't just download it all. You need to be able to explore it before you consider doing that. We'll be using an open source archive GUI toolkit called Firefly by IPAC that was originally developed for Spitzer, but's been extended in capabilities to meet the time domain science needs of WISE and NEOWISE, ZTF, and it's also used by Rubin Observatory. So all of those time domain capabilities will be used also by Ultrasat. Because of the proprietary period, we are going to be aiming the tools at variability science. Example, we have some tools already that focus on that. So we have a time series viewer and periodogram service, and I'll show you a screenshot of that next, that allow users to study both the images and the time domain measurements simultaneously and visualize them and calculate the period. We also have a forced photometry service that, for example, ZTF uses that allows, for any position on the sky, for an object to go and do forced photometry on the imaging data to get photometry at that position. And then we have an image coadder that we've used for WISE and NEOWISE. On this, where you can take the single epoch images and coad them at any level of granularity that you might prefer in order to, say, increase the signal to noise for certain objects, but yet keep some time information. And then I'm just going to end with a screenshot of the time series viewer to give you an example of the kind of tools that we're thinking about. So here we are looking at WISE data, NEO-WISE data, where a user has searched for, this happens to be an Lyrae star. And you can see that there are tables of both the raw data from the catalogs, but also the phase folded data. So this is just the WISE columns that you would get, but phase folded. And at the same time, you can see a plot of the data that interacts with the table. So if you look at any point on this phase folded data and you want to see where it came from, you can easily find it in the table. And you can also inspect the image from which it came. So you can manipulate these images and you can see if there's any outliers or any, large error bar ones, you can quickly inspect to see why that happened. So these are the kind of tools focused on variability that we plan to provide the community. So hopefully I stayed within my 5 minutes, but I'm happy to answer questions if I did it faster.
Okay, thanks, Vandana. I think we're running a bit behind, so what I'd like to do is go ahead and have Bob Blum come and speak, and then Valerie, and then maybe after that we'll pause and have at least a 5 or 10 minute, 5 minutes for programmatic questions before we move on. Bob, this should advance your slides once I get them up.
Okay. Oh, it's great to be here with you all. I'm Bob Blum, the Rubin Observatory Operations Director, and I'm going to give you a real quick swing through some of the discussions we've been having with the NASA folks and with ULTRASAT folks about collaborating with Rubin Observatory and the legacy survey of space and time. We're really excited. I mean, both of them, ULTRASAT and Rubin have a strong emphasis on transient science, and so it's a natural thing to think about putting together and working in ways that are very effective for the U.S. community.
We're going to need just a moment for me to get to sort out the slides.
Okay.
So.
Well, I can probably say it verbally. I only had a few slides. Yeah, so the first thing I was going to say is give you a really quick heads up on where we're at with the construction project and the schedule. We're expecting first light in July of 2024 now, so the schedule that the ULTRASAT folks showed us today, I think, is a real good one, because we'll be up and running, hopefully quite smoothly by the time ULTRASAT is ready to start producing its alerts. We have a camera that is fully integrated in California at SLAC, and we expect to ship it to Chile, hopefully in about May of this year. It needs to be tested end to end before we ship it, and so then we'll retest it when we get it onto the summit in Chile to ensure that everything is as it should be after it goes through that travel event. On the mountain itself in Chile, we have a fully working facility. There is a telescope mount assembly that is actually observing the night sky with a 35 millimeter camera on the top end. There's no sub-assemblies in it yet, but it is moving around the sky at night, so that gives you a sense of where we're at there. Within a month or so, we will start putting major sub-assemblies onto that telescope and testing them and integrating them to get ready for first light in 2024. The ULTRASAT program and the connection to Rubin is being done within the framework of our so-called in-kind contribution program. So Rubin is a proprietary survey to the US community and Chileans, but we have a very substantial international component built through this in-kind program. So rather than contributing cash or some other way of connecting with us, we've invited international teams to contribute to the observatory itself, either to operations aspects, that's actually fairly limited, or more generally to science-based contributions that connect very directly with our science collaborations and the Rubin community of scientists generally. And that, of course, includes all the US community that's connected to NASA. There's a host of different types of contributions, software contributions, telescope time, proprietary data sets, that kind of thing. Those are all the type of aspects that connect us to ULTRASAT. We have actually a detailed program that we've been working out with the ULTRASAT program of 3 contributions. You heard about one of them. We will directly exchange PIs so that US PIs will have an opportunity to be part of the science working groups of ULTRASAT. An equal number of PIs will be invited into the Rubin community and have just the exact same data access and opportunities as anyone else in the US or Chile. There is a contribution for the transient alerts. So we mentioned that the alerts themselves as they go out will be public, but there will be an opportunity for Rubin community folks to trigger on, say, a Rubin alert and go to the ULTRASAT and say, what is the upper limit, or what is the photometry of a certain point on the sky? Those triggers will be allocated through an open process through the Noir Lab TAC, just much like telescope time. There'll be a series of PIs that get access through that open call. They will get to drive what gets triggered on, but all the triggers will eventually, when they're done, will be made available to anyone in the Rubin US NASA community involved in this activity. And then there's a third contribution, which involves a UV sky map that'll be available. That wouldn't be the public data, but it would be a limited amount of data that would be available to the Rubin NASA community in the US. So those were the main points I wanted to make, and we'll have an opportunity to ask questions. The main point is we have a strong collaboration with ULTRASAT, and if you have questions about what that really looks like, come and talk to us. Send me an email at rblum@lsst.org, and we'll get you fixed up.
Thanks, Bob.
Yep.
Thanks for dealing with my technical issues too, Valerie. I think I'll be able to get your slides on this laptop, and you'll be able to page through them. This is the same issue that hit me at the beginning. My NASA laptop not only wouldn't share through the screen, but it wouldn't share to the other one. So I think this time
Thanks, James. So you've heard a lot about the ULTRASAT Participating Scientist Program already, and I'm just going to give you some details. So I'm Valerie Connaughton. I'm the NASA Headquarters Program Scientist for ULTRASAT. I'm not part of the ULTRASAT project. I represent the taxpayer, and my job is to try and make sure that the US community gets as much scientific value from our investment in ULTRASAT as possible. And one of the ways we're doing this is through this participating scientist call. So do I use the arrows to advance? Okay, very good. So these are the...
Can you also please sharing in the Zoom, because we are in the WebEx?
Sorry?
they've lost the share on.
Oh, I see.
Yes. Thanks, Ellie. Sorry for that. We'll screen it, just page to where you were, and then...
Very good, thank you. Can you see it now, Ellie?
Yeah, thanks.
Okay, very good. So some nuts and bolts about the program. This is the main vehicle for onboarding US members to the ULTRASAT science team, not just NASA members, but US members. The call was issued just before Christmas through an amendment called Amendment 81 to our omnibus call for proposals to the community, Roses 22. And I have a link here to the page that describes this element, D19, called the ULTRASAT Participating Scientist Program, which we call USPSP. That's the only acronym I'm going to try and use in this talk. The notice of intent to propose are due on January 23rd. These will not be reviewed by the peer review panels. I've had a few email questions about this already. This is really to help us to start forming the panels for the review, and also to help you help your proposal find the right panel, because when we know it's coming, we will have a panel assembled to review it. The proposals are due on March 31st, and the selections are expected in June. This is a really rapid turnaround. We're doing our best to achieve it, and the rapid turnaround is motivated on a desire to have the USPSP selected scientists participate in the ULTRASAT science team meeting that our Israeli colleagues mentioned in the previous presentation. Just a few peculiarities with the proposals that we are soliciting here. These are single PI proposals, so we're not looking at proposals from teams of co-Is and collaborators. The US selected PIs will be single PIs who are joining an existing collaboration, but of course their students and their postdocs in their group will also be welcome to participate in the investigation, but only the PI will be a participating scientist. Any kind of other collaboration between the US PIs and the ULTRASAT team are on the basis of discussions with the ULTRASAT team and not on the selection by NASA. But we can accommodate a science PI if, say, an early career researcher isn't able to propose for institutional reasons as PI themselves. The proposals are 6 pages, which include the reference for the science technical management section. You don't need a data management plan, and you don't need an anonymized budget. So a lot of you are familiar already with our dual anonymous peer review process. And there have been a couple of changes over the last year. Now you don't need to have a separate summary. The summary for NSPIRES is now included in the anonymized proposal provided to the peer review panel. And the other thing I want to draw your attention to is that because you will be, if you are selected, you will be joining a team. This means that the expertise and resources document that you provide in a non-anonymized format, which the peer review panel will look at after they have evaluated the scientific merit of your proposal, becomes very important. So I'd like you to consider that you need to think about how you could demonstrate in this document your qualifications and your capabilities to work as part of an international team within an existing working group structure. And again, don't submit a budget in the anonymized proposal. You submit your budget separately. And that means that the cost reasonableness of the proposal is really evaluated looking at your proposed work plan and also your proposed work table and your level of effort. The program itself, as I said, this call will select US participants for the ULTRASAT science team. So it's part of an agreement between NASA and ULTRASAT, but it's also part of an agreement with Rubin and ULTRASAT, as Bob was just telling you. And NASA has funding for a subset of participating scientists, up to 10, but will select up to 14, depending on the final agreement that Bob and his team have with ULTRASAT. The participating scientists who do not receive NASA funding may opt to look for funding elsewhere, and they may also opt to apply for the NASA program and not apply for funding, already saying that, I have a better chance of getting funding through another opportunity. So that's something that you will be able to select at the time you submit your proposal. The selected scientists will be part of the working group structure, so either as part of one of the existing working groups, but if you propose science that is so wonderful and not already considered by the ULTRASAT science team, a new working group may be appropriate, and that's something that is not disallowed by the call, but you need to convince a peer review panel that your science is worthy and nobody else has thought of this science area. The PSPs will serve 3-year terms. So at the moment, the 3-year term should cover the first 6 months of ULTRASAT science operation. We hope to be able to extend the performance of the selection should there be some launch delay, and should funding allow us to extend the funding so that 6 months of that term are covered. And then we expect to issue a second call to cover the complete prime mission, subject to funding being appropriated by Congress. And existing PSPs will be eligible to apply to that second call. And I think that's all I have. Yep, that's it.
Take 5 or 10 minutes and see what questions we have in the room on the mission generally or the programmatic aspects that we've just been discussing, collaboration.
Do you want us up here?
Why don't you join me and
Yeah.
we'll see others can join if they wish what the questions are. So, first question. Thanks. Yeah, go ahead and use the mic for people outside.
Thank you. This is Enrique Flashback from NASA Space Center. I'm curious if you were also considering a guest observer a program at a later point, or if this US participating scientist program would really be the only way for people
James, we cannot hear you at all. Can you somehow either repeat the questions or?
Yes, so the question was whether there will be a guest investigator program in addition to the participating scientist program. And I believe the participating scientist program is the mechanism for US scientists to get involved. And that will include, going to team meetings, joining the working groups, and being able to advocate for where you think it would be a good idea to point ULTRASAT. But I don't think there's a separate call anticipated. Avisay or Iair?
Let me just say that within the team, everybody is treated the same. So US PIs will be the same as Israeli PIs, German PIs. We do not offer GI type program to anybody.
So I did not hear what was said, but I agree with what you said, James.
Okay. A question at the back. I don't know, the microphones in the room seem not to be talking to Israel, so. Yeah, Tom, if you just come up and use the speaker's mic here, then Israel can hear as well.
Okay, my name is Programmatic. So Tom Barkley from NASA Guided. Two questions. One is, you talked about the document describing your capabilities. Does that mean the proposal review is different from a regular NASA review and includes the Israeli side reviewing the proposal, or is it just a regular NASA review? Is the NASA review just a normal NASA peer review, or do the Israelis have a review component?
It's a normal NASA peer review, but it's done anonymously, and so the panel will review your anonymized proposal, and then after the evaluation is complete, they will see the expertise and resources, but it's still part of the NASA.
Okay, and then the second question I saw on the earlier slides, it says there's 8 NASA participants and you had 14 NASA participants. Does that mean that some of them are coming from Rubin? Does that mean there's already a pre-decided that 6 of the proposals selected will be Rubin specific?
So it's a unified call.
Can you also speak to the mic so we hear you?
Can you hear through this microphone? Okay, good. So it's a unified proposal call. So from a NASA relevance perspective, if it's relevant to ULTRASAT astrophysics, it's relevant to NASA. So in principle, we could select 14 people who are doing Rubin and ULTRASAT science. But we're doing it based on science, not based on whether you're using Rubin or not. Did that answer your question? Yeah.
Yeah, and I could just add that one of the key elements of our international in-kind contributions program is to benefit U.S. science. We expect the vast majority of contributors to want to engage with Rubin, but the main point is to have a unified, in this case, scientific program and let the community come in and do what they want to do, and that is what makes the exchange work.
Just add that, as we said, as all other APIs, eventually all APIs selected are approved by the ULTRASAT Science for this is again for also for Bulgarian and German APIs, where NASA and Rubin.
Yeah, Benjamin. Yeah, why don't you come use this microphone because we know this one works.
Sounds good. I have two questions. One, so the TOOs, they come out of the working groups. Is that how they'll actually be triggered, or are there public TOO requests that can come in from the outside?
I think
So, for the TOs, they will be decided by the working group science and approved by the science board. So far, we plan on TOOs for gravitational wave follow-ups. Additional science cases would have to be developed within the working groups and approved by the science board. We have a science board which includes representatives from all the participating funding bodies. And if there is a strong case for a different type of TOOs, we would consider it and probably approve it.
I was also curious about the thermal stability and its related PSF stability. Is there any expectations? Obviously, that goes into photometric precision over time.
So you were asking about the thermal and PSF stability?
Yep.
Okay. So I think it's best that Yossi answer this, or either Eran wants to jump in. Yeah.
So, I mean, in terms of pointing stability, this is not the limiting factor. So it will be less than 3 arcsecond for a 300 second exposure. So this is not the dominant factor. In terms of temperature, so we have a very strict requirement of the operating temperature. So it's 200 Kelvin plus minus 5 Kelvin. And we actually, according to our current designs, will be probably within plus minus 1. So we don't expect to have any degradations, but we obviously will calibrate it during the mission.
Yeah, but the bottom line is that the contributions of stability, thermal stability to variations in the PSF are expected to be small. And I think we have a good modeling analysis of these effects to be confident that this is going to be the case.
So there's a question from the crowd as well. You present the limiting magnitude, but I didn't see any requirements or anything on any of the slides for the photometric precision over time. Do you have an estimate for what the photometric precision should be?
So this is exactly for Eran to answer. Eran.
Yeah, the answer is I don't know, but since this is a silicon detector, I expect that it will behave as good as other silicon detectors, and we will be able to get close to the Poisson limit of the system. The only question is what kind of systematics effect will when we'll start to see systematics effect. Because we don't have any atmospheric effect. This is probably much better than any ground-based observatory. But in any case, you have to remember another thing is that ULTRASAT is, if you compare it, for example, to Kepler, it's a smaller telescope, so the number of photons involved in any process are smaller, and therefore you can do very high precision only for very bright sources. I will just give you another quantity that may be interesting. It actually was in Yossi's slides, that at the bright end, the expected signal to noise is of the order of 1000. So we are talking about 1 millimag precision, and I don't see any reason why we cannot achieve it.
Thank you so much.
Okay, we have one question online, and then I'd like to get to the science presentations before too long because we have 30 minutes of scheduled content and I want them to have some time for questions too. So the online question from Paolo Coppi is the time allocated to the 200 square degree fast cadence survey and the 8,000 square degree survey cast in stone? Can it be changed during the mission? I'll pass that to Eli, I think.
Yeah, so hi, Paolo. No, it is not cast in stone. We will certainly follow this plan for the first 6 months until we understand our performance and limitation. But after this period, we would be open to negotiating, to discussing other observational plans depending on the science justification. So this will be certainly the operation plan for the first 6 months, but then we would be considering changes according to the science cases raised by the working groups and approved by the science board, etc. And after we understand better our performance.
Okay, there are 3 or 4 more questions in the chat. I might suggest that we answer those in the chat during the next few minutes, those of us who have those answers at our fingertips. And is there a last question in the room before we hand over to Avisay to kick off the science part of the discussions or presentations? Yes, one last question.
Hi, this is just a quick question about the concept of operations. I guess, so you have real-time data, you're bringing it down, you're going to issue alerts to the community, but how does that intersect with your planned schedule? So like if you find a shock breakout, right, in an alert, will you dwell on target or will you just continue on? Like, how will you maximize the effect of these alerts on the operations?
Okay. Hi, pleased to see you there. So we will modify the observing plan following detections of transients and also following TOOs that will be triggered by other instruments like GW. Now, there would be a continuous cycle of planning observations. Each time there would be a new detection. There would be a new program approved by the operating group here at Weizmann. And we will decide how much time to allocate to follow-ups and with what cadence and so on, and what other parts of the observation plan to postpone in order to accommodate this.
Right, but so I guess to clarify, that loop sounds like it's longer than you would require to stay dwelled on a particular field if something interesting was there.
Well, I'm not sure I understood your question.
Step in for a moment. The question basically is about responding to things and whether you stay on a target when it turns out to be interesting. And I think given that about 20 hours a day of the current operations model is to stay on one field with continuous 5-minute integrations, that's, for 80% of the transients that are found, you'll already be dwelling on them for continuous coverage for 20 hours, which is probably long enough to respond if you decide you really need to extend it to continuous coverage for 72 hours or something. I think a lot of this remains for future discussions when things are up there and we know the on-orbit performance. So I'd like to hand over now to Avisay Gal-Yam, who is going to talk about the role of ULTRASAT in the time domain ecosystem and some related issues. And then we have a series of 6 science shorts, which will be 3 to 5 minutes each. And we'll try to hold questions on the science also till I think the end of the science block. And now I just need to find my share button and my PowerPoint, and I'll hand it over. Microsoft PowerPoint. Whose PowerPoint will it be if I just do that? One moment. That is Valerie's. I will close out. Oh, right. I need to. All right. So, yes, open. And share. Right, and now. Okay.
Thank you, James. Hi, everyone. So the goal of this short presentation is to try to highlight a few things that explain the impact of ULTRASAT on the TDAM ecosystem in the US, also elsewhere, of course. And I think the main point, in my opinion, that Ultrasat will have a fundamental, broad, lasting, and even revolutionary impact on this community, and I will show you why I think that way. I will focus on 4 aspects, which I called Ultrasat as an instigator, localizer, classifier, and as a background. I think that will become apparent immediately. So let me begin with an instigator. So a big impact of Ultrasat will be to provide alerts, of course, but if you stop to think about it, I think it will change the way we consider studying a transient. So what I'm showing you on the screen is the best of the observed transient from ZTF, in my opinion. This is 2018 GEP, where this supernova was discovered during the rise time, during the night, and follow-up was initiated immediately. If you look on the right side, you will see what sort of coverage we have in different bands. And what I wanted to highlight is that really only in R and G band that were provided automatically from the survey, you really have coverage of the rise very well. The rest, even though the follow-up was initiated immediately using a large network of telescopes, is patchy at the beginning and only becomes better later on. Ultrasat will provide the same thing from the first few minutes for everything. So I think the way we look at supernovae or other transients will change. So the time of the beginning of the event, which we usually call T0, will become something that you really know and not one of the parameters you should estimate. And things like the rise time, which hold a lot of the information about the physics of these explosions, will become very well defined. So rise time is the time from event to peak. Right now we estimate it in all kinds of other ways. So I think this will be a significant impact. Of course, Ultrasat will not provide this for every transient in the sky, but it will provide this for a very large sample of transients, hundreds, and over the mission lifetime, perhaps even 1,000. Another thing that is difficult, important to consider, the UV usually is detected for most events which are very hot initially before you can see it in the optical, even with instruments that are sensitive. What I'm showing here is an example from a pre-Ultrasat experiment we did with GALEX and PTF. So GALEX was doing UV from space, PTF was doing visible from the ground. And in all events that I'm showing here, these are 6 supernovae that had shock cooling flares. GALEX saw this 1 to 2 days before it was detected from the ground by PTF. PTF is a bit more sensitive than ZTF. So basically, once you see it in the UV, you can already start observing the right location, even if your instrument is not seeing the signal in visible light at this time. So I think people really can start thinking about what they want to do, how they want to study a transient, even before it's actually detected with their instrument. I think this is going to be a new thing. It's a little bit similar to what we have now with gravitational wave sources, which tell you something interesting is going to happen, but you don't know exactly where it is. Here you will know exactly in which galaxy it's going to happen, and similarly with the GRBs before that. On the right-hand side, you can just see how much more UV light you get. This is from a model, but as I said, it's actually confirmed by observations. Moving on to Ultrasat as a localizer, this is quite obvious and already was mentioned. So Ultrasat will be great at localizing events that are initially poorly localized, like gravitational wave sources, but also neutrino events, other multi-messenger events. 200 square degrees is a large field of view. We will have references over the entire sky, and we can really pinpoint rather rapidly, I think, the right source to target, and this will be available immediately to everybody. As I said, there's also, and also explained before, it has an almost unlimited TRO capability. It needs to be approved, but in principle, technically, it can follow a very large number of triggers from all kinds of different sources. Another important thing to remember, especially when you're doing multi-messenger studies where you know the time of event very accurately, for example, with neutrinos, gravitational waves do better than a second, but the location is known very poorly, and you try to determine if something is related or not related to a source that you are seeing. Knowing the time accurately also for the visible or UV light is very important. Right now, typically there is an uncertainty of at least a day and often many days about when something happened. And here, at least within the Ultrasat field of view, you will have events where you know the time of event to an accuracy of minutes. That will enhance the ability to do cross correlations with low number statistics messengers like neutrinos linearly with the improvement on the knowledge of the time, which is at least a factor of 10. So the number of, let's say, significant neutrinos you need to establish in a correlation could go down from tens now to few. Moving on to ULTRASAT as a classifier, as I'm trying to cover here a wide number of impacts. On the right-hand side, you can see to my knowledge, the earliest spectra of supernovae that we know of. At the top is a type 2 supernova. The red curves are black body fits. This is hotter than 20,000 Kelvin. In the middle, there's a type 1c supernova associated with gamma ray burst from 2006. This is 2006 AJ. The temperature of the type 1c supernova at this time, which is a few hours after the event, is approximately 11 or 12,000 Kelvin. And 2011 FE, which is amongst the earliest and probably the best observed type 1a supernova ever, the early spectra are much cooler. They are about 7 or 8,000 Kelvin. So if you extend this a little bit to the left where the near UV is, you will see that the near UV versus visible colors are very strong discriminant of supernova type. The same is true for other sources of events like superluminous supernova that remain hot for a very long time, TDEs that stand out in the temporal behavior of the temperature, which is something Suvi Gizari pointed out a few years ago, and this is a very good way to select them and so on. So the combination of ULTRASAT with things like Rubin will be very powerful to select and optimize how you, the astronomer, want to spend your resources. So if you're interested in a certain type of event, you will be able, with this combination of information, to select a sample of events you really want to spend your resources on. The last aspect I wanted to discuss was the background information ULTRASAT provides. This was also mentioned by Bob. We will have this very uniform and deep UV map of the entire sky, deeper than GALEX and also without all the holes that GALEX had for all kinds of technical reasons. And the type of galaxy something happens in, there's a demonstration there on the right-hand side. Fitting the SED, you can have parameters like the mass, the star formation, and so on. And different types of supernovae and other transients happen in different types of galaxies. So the galaxy information actually tells you interesting things about the physics and the progenitors of the events that you want to study. This is a rather famous distinction between superluminous supernovae that happen in lower mass, higher star formation galaxies than other types from Schultz et al. From PTF, and there are similar studies from other sources. ULTRASAT will be sensitive to rapidly evolving transients, redefining the meaning of rapid. So this is from a recent paper by Anna Ho, and it shows that the most rapid transients, with extragalactic transients we are currently studying, are of order a few days. And ULTRASAT will have the sensitivity to discover transients that are on timescales of hours or even less. We don't know what they are because nothing else has this sensitivity except for gamma ray bursts that we find in gamma rays, but any type of events that emit only lower energy photons, we don't know what they are, and I'm expect that we will find some exciting new things. This is what I call the Kepler effect. So continuous observing at high cadence is very powerful. This is a nice paper from Armin Rest, who's studied a rapid transient with Kepler, and you can see the very full description of the light curve. It's very, very interesting. And actually, it's the only one we have because it just happened to happen in one of the Kepler galaxies at this sort of level. ULTRASAT will provide similar data for many, many types of objects. And as you can see, you can look for all kinds of interesting features on the rise, including shock breakout, but not only limited to that. I don't want to go into the details, but if you can follow the slide, information about the temperature and the luminosity tells you how the effective radius of the emission changes with time. And this is a very strong discriminant between different physical models. There will be all kinds of additional science. Intentionally, I want to keep this short, so I don't want to go into many different examples of the flares and bumps and late time and early time changes that you can find in all kinds of things. But the main thing you can think about ULTRASAT is staring at the same location in the sky almost continuously with very small gaps for 6 months. So some of the things we are now finding happen which we didn't find before because we weren't looking. So there was an event, it went away, we stopped looking. ULTRASAT will continue looking, we don't have to remember to do this, and quite often we find things that rebrighten and so on. So let me stop here and then we will have a time for questions later on.
Thanks, Avisay. So I believe the first of our science shorts is Iair Arcavi, who's speaking remotely. Let me find the stop share button if I can. Oversharing is a real risk with the current way of doing things. Okay, good. Looks like
I think I took over. Okay, can you hear me okay and see the slides?
I can hear you, and I'm putting it full screen, so. Take it away.
Thank you. Okay, so hello everyone. So we're used to thinking about kilonovae or gravitational wave counterparts as infrared mostly, but it actually turns out, according to the one event we saw at least, and new models that came after it, that the UV is not only detectable but also crucial for understanding the physics of these events. So actually the 170817 kilonova light curve turned out to be a little bit more complex to explain than we thought. Explaining all the bands at all the times cannot be done by a single radioactive decay component, which was the fiducial model for these things. One reason for that might be that kilonovae don't have a single ejecta component, but are actually expected from numerical simulations to have at least 3 different components. Red emission coming from the tidal tails, blue emission coming from polar ejecta, and either blue or red emission coming from post-merger winds. And each of these emission components have different masses, different velocities, and different opacities depending on their composition. And so they will affect the light curve, contribute to the light curve in different ways. And if we can disentangle this, we can get a huge amount of information about the merger and the merger physics, including concerning masses, nucleosynthesis products, and so on. However, there are other competing models to explain the different emission components that we see. And it turns out that the UV is crucial in distinguishing between these different models. So here you see bolometric luminosity at the top of the 170817 kilonova, temperature and radius. If we focus on the bolometric luminosity, and especially on the first point, you will see that actually the models are 2 groups of models here, those attributing the emission to radioactive decay, the red models, and they kind of rise on a half-day timescale. They're still rising or peaking, versus shock cooling or other blue emission mechanisms which are declining already from the first few hours. And we can't actually tell which one is correct because the first bolometric data point can either be up here, consistent with the blue models, or down, consistent with the red models, and actually it does not distinguish whether we were rising or declining on 0.5 days post-merger, and that is the discerning factor between the models. And the reason we can't tell if it was declining or rising, if it's the bottom point or the top point, is because we didn't know what the UV was doing at that critical moment. The UV holds the key to what the bolometric light curve does at the early times, and that holds the key to distinguishing between the models. So UV is very, very important, especially at these early times for distinguishing these models. Another component on the UV will contribute to the UV, theoretical, not yet observed, is the decay of free neutrons from the leading part of the most rapid ejecta. These decay on time scales of about an hour. You're seeing here model light curves by Brian Metzger, and you see that they are brightest, this flare is brightest in the UV, and detecting this can actually help constrain physics of the ejecta, its structure, and the amount of mass and free neutrons, and this in turn constrains a lot of the models of these mergers as well. So it's a separate emission component that the UV is the most sensitive to. And I'll just end with a third importance of UV, and that is actually in distinguishing the elements seen in the spectra later. So these are the spectra of the kilonova, and there is a debate whether the feature you see there is coming from strontium or from helium. And this, of course, informs the nucleosynthesis synthetic yields deduced from this event and the R process that's going on. And models claiming that this is helium can only work if there is a weak enough UV flux at early times to not ionize the helium. And so knowing the UV flux at early times can even help interpret the features we see in the spectra later on. So I'll just summarize and show you just 3 example things of how UV emission is critical for constraining neutron-star merger properties. It can distinguish between emission mechanisms and ejecta components. It is the most sensitive to early free neutron emission, which is on timescales of hours, and it can help with element identification in the spectra later on. So thank you very much.
Okay, I think our next is Jonathan. Jonathan, you're the next, right? Jonathan Morag will be telling us about early supernova predictions. And I need to share the right thing again, sorry. This will take a moment, but I'm doing 2 of them together so that we won't have to pause between Jonathan and Ido. So there's that. And then we need to go to WebEx, find the share button, which is there, share a PowerPoint, share, and we want to enter full screen and hit the show button. I think you're on.
Thank you. You guys can hear me okay? Hi, pleasure to be here. My name is Jonathan. This is work that we did with Ellie. This is theoretical work on supernovas. What I hope to convince you in the coming minutes is that we have an analytical formula that hopefully you can use to extract real meaningful information from your data. So, when you want to extract information and discern the properties of the star or system of stars that spawned your supernova, of course you need to catch it early on in the act, as has been said here before, especially in the ultraviolet. And you also need an analytic model that you can trust that can help you extract the progenitor radius, the energy per unit mass, the extinction, and perhaps other system properties. And so this is what we give you. An analytic description of the shock cooling emission, which is mainly thermal in the first hours and days of the emission. And we calibrate this formula to numeric simulations spanning a large parameter space. And you see here the parameters we vary, among others. We include a realistic opacity, which hasn't really been done in the analytic works. And we account for deviations from black body emission. Our formula is based on certain assumptions that won't work for all the supernovas. But the key hope here is if we take a simplified system and we give a very clear prediction for what you would get, we hope that you'll be able to use it to confirm or reject the assumptions on which it was built, which is something that we don't get to do often when we compare astrophysical models. So a little bit of detail about how we did this. Our numerical simulations, they're one-dimensional, hydrodynamic, radiative diffusion simulations. They're multi-group, which means that we relaxed the assumption that the photons are in local thermal equilibrium. And we solve separately the physics. We bin the photons into frequency groups, and we solve the physics for each frequency groups separately. We have our own frequency-dependent opacity table that we built for this purpose. And we check convergence, and we reproduce numeric results from the literature. The result is 2 analytic formulas for the spectral energy distribution. The first is an approximate black body solution with bolometric luminosity and color temperature. And then we also give you a frequency-dependent formula that accounts for small deviations from black body emission. So this is an example of the frequency-dependent opacity that we get in our table here at right. So this is the absorption opacity as a function of frequency at a particular density and 2 different temperatures. And what you're seeing is the the free opacity, and you have atomic lines and photoionization. This table is going to be publicly available for your use. Opacity is an important source of uncertainty in our problem, so we were very careful about using it and comparing it to other tables. I won't say much more than that. I'll go on to show you results. So here's a comparison of the simulations with our analytic formulas. So these are multi-group simulations. This is the spectral energy distribution as a function of frequency at 3 different times. Can you guys see my cursor maybe? Yeah. So the simulations are in color. What you see in blue is 1 hour, 1 day in red, 1 week in yellow, after the shock breakout. We compare this to our simple black body formula in black, which you see already has quite good agreement. And there's no additional fitting in what you're seeing here. This is based on the parameters of the problem, and that's it. Even though there's good agreement, you do see there's 10% deviations in the Rayleigh-Jeans regime. And you also see UV suppression due to line dampening. But in fact, we also have a formula that describes these deviations. So here you're seeing 2 examples at very low injection energies and very high injection energies. It's the same legend. Simulations in color. Our black body formula is in black, again, without additional fitting. And now I'm showing you it in dashed lines. I hope you can see it. You're seeing our frequency-dependent formula. And you see that it does a good job of describing the deviations from black body emission. And you see this in both examples. Okay, so we did this for many simulations, different progenitor radii, different masses of core and envelope masses. And the story is sort of the same. Black body emission is a good description. And we have frequency-dependent deviations that we do, I think, quite a good job of describing. And to summarize, so we derived accurate analytic expressions for shock cooling emission in the first hours and days of the supernovas. It contains 4 free parameters, and it's derived from first principles. And we hope that it will be a useful tool for inferring system properties using early multi-band shock cooling observations, especially with ULTRASAT. And ideally, especially if you had a good model for some of the more fancy things with wind interaction and all sorts of stuff, you could use this to confirm or reject the assumptions that we put into this formula. And you can hopefully extract meaningful information from your data. Thank you very much.
Next speaker is Ido Irani, who's following up with the observational aspects of this.
Okay. Hi, everyone. My name is Ido. I'm a student with Avisay, and I'm hoping, if you weren't convinced by Jonathan's talk, I'm hoping to convince you myself that we'll be able to actually infer interesting supernovae properties from observations using ULTRASAT. So, as you've heard in the previous talks, the early emission from a supernova can constrain the progenitor properties of these supernovae. On the right-hand side, you can see model light curves in UV in purple and red for 3 different progenitor types. And we're actually sensitive to the difference only in the first few days. So ULTRASAT is the only survey that can give us the answer to discriminate between different and measure these different radii of progenitors using the light curves. So that's great that the model can give us this kind of answer, but can we actually fit this model? And it's actually quite a difficult problem involving many biases. So I won't have time to tell you all about this, but we've developed a method to actually fit these light curves. And we can test ourselves by fitting the multi-group simulations that Jonathan has developed. So on the right-hand side, you can see an example. On the left is a fit for a multi-group simulation, and we managed to go back to the real model light curves. And on the right-hand side, you can see that this fit is representative of what we would get for a real supernova previously published in the literature. So we can do it. We can fit supernova light curves. We repeat this process for over the entire parameter space of the simulations, and you can see that we managed to fit the radii and get back the same radii with a reasonable uncertainty over the entire parameter space, which is 2 orders of magnitude in radius. So that's good. We can fit it. We can get the right radius back from the simulations. Of course, sampling will have a huge effect. If we compare an ULTRASAT-like observing strategy to a ZTF-like observing strategy, we would get much better uncertainties using an ULTRASAT plus ground-based data set with a sampling uncertainty of about 25% in radius compared to 75% in ZTF. So in addition to having many more supernovae, less observing bias, we'll have also much better constraints of the parameters using ULTRASAT. So this is a big step towards having a sample of progenitor radii from the supernovae datasets. In addition to this, we're also going to look at early UV emission from type 1bc supernovae. On the right-hand side, you can see an example of one such case that we've recently published. There have been several previously detected such early UV flares on a day time scale. And we're probably only seeing the lower and the brightest and slowest end of the distribution in terms of these UV flares in the early times. And we suspect these are connected to CSM. So it would be very good to map the entire landscape of ULTRASAT and detect some weaker and faster bumps to characterize the CSM around 1bc supernovae progenitors. So I'll leave you with a summary slide. Please read our paper on this 1C. And thank you.
Thanks, Ido. Our next speaker is remote. It's Sagi Ben-Ami telling us about M-dwarf flares. And I think you can just grab the share from me and start sharing.
Okay, can you see?
We can see, and I will be just full screening it in the next few seconds, but I think you can begin when you want to.
Okay, so my name is Sagi Ben-Ami. My main role in ULTRASAT is actually leading the payload design, but I'm also leading the exoplanet and planet interaction and stellar interaction group along with Yossi, the project scientist. And I'm going to switch from the transient world into stellar flares, which is another topic that ULTRASAT can really contribute significantly to our knowledge. So we know that M-dwarfs exhibit flares with instantaneous flux of up to thousands of times their quiescent flux. And you can see on the right spectra taking during a flare in the UV from probably our best example, Ido Irani. During the flare itself, you can see how much the flux is rising during the impulse phase. These flares are often accompanied by solar energetic particles. And you can see here on the left side the relation between the energy of the flare and the estimated fluence of protons on the surface of a hypothetical planet. Overall, this results in the fact that M-dwarf habitable zone planets are exposed to high energy radiation and high flux of energetic particles. Now, UV radiation as a stressor can have a significant effect on the planet, on a planet atmosphere. It can lead to planetary atmospheric escape due to short wavelength radiation and heating of the planet exosphere. If it is accompanied with coronal mass ejection and solar energetic particles, then it can actually erode the atmosphere from molecules that provide atmospheric shielding. And if this really happens, then we can result in the surface of the planet being highly radiated by UV emission. And you can see on the right the difference between the top of the atmosphere radiation for an hypothetical exoplanet versus the surface radiation, assuming that he has an atmosphere that is similar to that of the early Earth. So there's a very big difference in case that we have erosion of those atmospheric shielding. Now, from the search of biomarkers perspective, then UV radiation can actually cause a biotic source for biomarkers, for biosignatures, such as molecular oxygen. There's this wonderful works by Meadows et al. That shows all kinds of paths that might lead to the presence of O2 and ozone in an exoplanet atmosphere that is actually not related to the existence of a biosphere on that planet. Many of those paths are actually caused by photolysis from near UV and far UV radiation. For example, the case of the ocean loss in M dwarfs, in which UV photons actually break water molecules. The hydrogen molecules are lost from the atmosphere, and molecular oxygen and ozone is actually generated on the atmosphere of that planet. Now, so far we were discussing the sort of bad implication of UV radiation for the habitable zone planet, but there's actually also a necessity for high energy radiation from the point of view of prebiotic chemistry. So the only viable path that we know today for the generation of the prebiotic molecules required for RNA are involved, require an energetic source that is the UV radiation in the early Earth. And you can see on the right side here the chemical network that will lead eventually to this RNA pyrimidine. And this path actually includes two reactions that require the presence of NUV radiation, and the flux in the NUV actually needs to be high enough in order to overcome thermal effects that are marked here by these dark arrows. And if the thermal process, the thermal branch is actually much stronger than the photochemical process, then we won't result in enough prebiotic substance to actually kickstart the RNA world as we know it. Now, from studies of the quiescence emission from M dwarfs, we know that we are missing several orders of magnitude when we compare the emission, the UV radiation emission, the UV radiation environment on a hypothetical exoplanet surface compared to the young sun, compared to the early Earth. And you can see here on the left side the young sun compared to several known exoplanet and stellar hosts that already been investigated. Now, the flare frequency distribution of M dwarfs have actually been studied by several groups already. The two leading ones is the Muscle Survey, led by Kevin Franz, and the Azimuth survey, led by Evgeny Shkolnik. In the right side, you can actually see, I know it looks like the same paper, it was actually also written by the same person, but it's actually two different papers, one from Muscles, the other one from Azimuth, that were published on the same day, by the way, showing the flare frequency distribution in the far UV. And you can see in the right side that when you actually measure the flare frequency distribution in equivalent duration, it actually looks uniform both for early stars and late stars, and both for what we call active stars and dormant stars or inactive stars. And that leads us further to study the flare frequency distribution in terms of equivalent duration, because it allows us really to have a one rule fit them all for the FFD. Now, several surveys, well, this one is mainly based on HST data. Several surveys have taken long baseline observation of M dwarfs that allowed us to measure the FFD, GALEX, TESS in the visible, and there's also two CubeSats that are now targeting long baseline observation in the UV for specific targets. That's the QUT led by Colorado, by Kevin Franz, and Sparks that is expected to be launched soon, I assume, led by Shkolnik. Now, the results that we found so far indicate that the flare frequency distribution is very different at various bands. And you can see here on the right side, on the top, you can see the flare frequency distribution from the Muscle Survey in the far UV. And then in red and blue, you can see our analysis of GALEX data that shows the flare frequency in the NUV. And you can see that it's both different for stellar types, and it's different than the one shown for far UV and the one shown in the visible in the bottom based on the test data. However, due to limited data set, we cannot determine the flare frequency distribution in the UV bandpass for frequencies well below 10 to the minus 1 flares per day. We even have a bigger problem when we are investigating late type M-dwarfs, M4 and so on. We have very little data, and this is exactly where ULTRASAT will allow us to, will come into the picture, allowing us to monitor continuously or at a very high cadence in the NUV in many stars simultaneously. Now, this large instantaneous field of view in each exposure will have thousands and thousands of the order of actually 200,000 or 150,000 M-dwarfs in each exposure. Now, the vast majority of those are not going to be detected, and you can see the ULTRASAT AB magnitude histogram on the left-hand side for a given field, for an exemplar field. But we do expect that every 300-second exposure will have 75 M-dwarfs detected due to enhanced activity, due to them being actually flaring. 25 of them will be of early M-type, and around 50 will be of later M-type dwarfs. On average, we will be able to see of the order of 20 sources detected in quiescent as well, while thousands will be, for thousands of stars, we will be able to determine the quiescent flux with coads from the entire survey. Now, while ULTRASAT long integration raised challenge in resolving a flare profile, it will allow us to determine the flares of very high energetic and rare events. As you can see on the right-hand side, we took two of the most energetic flares that we found in the GALAX database and just bind them to the exposure time of ULTRASAT, and you can see that those are easily and readily detected in each image, and therefore will allow us to really determine what is the flare frequency distribution for those rare events that happen maybe once a month, maybe even once a year, but will actually have a significant effect on the atmosphere of a nearby planet, on an habitable zone planet, with a large number of stars that we will be able to monitor and study. We will actually be able to compose an atlas that will tell us which stellar hosts are more likely to harbor habitable planets, and then target those for specific studies, specific spectroscopic studies in order to detect biomarkers and study their atmospheres. That's about it. Thank you.
Thank you, Sagi. So I want to apologize for running late. We do have two more science shorts. I would love to give those speakers a chance to speak. And this is on me for packing too much into the session, but I'm going to go ahead and pull up Arielle's slides, and anyone who has to leave, we will understand, and I'm very sorry that I didn't have my act together with WebEx as well as I thought I did. But it's Arielle Weinstein who's going to be telling us about galaxy count predictions, and then after that, the last talk is Eran Ofek talking about lensed quasars and using them to using ULTRASAT to learn about lensed quasars from studying their time variability. So two exciting talks, and in a moment I will find my share button and hand it off to Arielle. Okay. Yes, full screen. Good. You go.
All right, so I'm just going to quickly talk about just some of the galaxy count forecasts that ULTRASAT is expected to see when it gets up and running. So these are just based on some preliminary research on GALAX and Hubble Space Telescope galaxy counts, essentially examining those those papers and those findings, and then using those parameters to generate ultrasat number counts based on that data. And this is essentially what ultrasat is expected to see. The higher latitude fields are in green, and then lower latitudes in blue, and then lower cadence counts in yellow, and the deepest field in red. These are cumulative galaxy counts distributed across the magnitude range of around 14 to 26, distributed in 0.1 magnitude bins. And then just going off of that, but there are some crowding effects that come into play. Ultrasat can't realistically be expected to see all of the objects in its field of view because of some objects that are brighter, which will impede the light of others, making it difficult to differentiate between them. So there were simulations run, as well as some analytical calculations to estimate the crowding effects, and these are described in this figure. These are the analytical calculations. Essentially, the pink box on the left correlates to the one on the right. And so to the left of that pink box, the effects of crowding won't realistically come into play. And then in the pink box, some objects will be lost, and to the right, nothing really will be able to be seen. That is basically it. Thank you.
Thanks, Arielle, for covering a little schedule. And the last of the science shorts is where are we? Number 13. Go for it. Eran, yes. We see your screen.
So ULTRASAT will provide us with a very large number of photometric data points for a large number of quasars. So, and this will be almost continuous light curves. So there are two opportunities that we think that we can follow with ULTRASAT. The first is for detecting lens quasars and simultaneously measure their time delay. And the second is measure AGN's black hole mass via AGN reverberation time delays. However, this has to be done with, given that the ULTRASAT resolution is poor, in this sense, for most lens quasars will not be resolved by ULTRASAT. And the second is that ULTRASAT has only one band, which again is a limit for AGN reverberation mapping. But I would like to convince you that this is probably doable. So I will start, and this is based on two papers that we published 3 years ago. I would like to start with the first problem, which is the second paper, which is how to detect lens quasars using the unresolved light, combined light curve from the sources. So the idea is very simple, and is to use both the combined light from all the sources and the center of light position of the sources, which basically these two observational properties allow us to break this degeneracy and actually reconstruct the individual light curves. This can be done either in Fourier space or in a time or in the time domain. Just for simplicity, it's easier to talk about the Fourier space, and I will mention this later. On the right-hand side, you can see some simulated performance, and if you look at the bottom plot, you can see the recovered time delay and flux ratio using this combined flux plus astrometry method. However, the preparation for the next method I'm going to discuss on the top plot, you can see what happens if you use only the flux, the combined flux. And the idea here is a bit more complicated, but the idea is that the question I would like to ask is, assuming that we have a light curve, which is a linear combination of, let's say, two light years, which are time delay, time shifted from each other. The question is, can we tell if the light curve was generated from such a process, and if so, to measure its time delay? And the general answer to this question is no, we cannot do it. However, under some, in some cases, we can do it, and this requires two things. One is that that we will have a statistical model for the light curve, and the second is that the light curve will power on a broad range of frequencies. And it's easier for me to demonstrate this in Fourier space. In Fourier space, AGN have a very strict light curve statistical model, which is the light curve is basically generated from a power spectrum. So if you take the power spectrum of the light curve of AGN, it will be just roughly a power spectrum with some noise on top of it. Now, if you have a time delay process involved, then this model in the Fourier space is written on the left-hand side and actually shown graphically on the right-hand side. It's becoming a power law on which a periodic function is superimposed. So basically, we can fit it, and we can write the likelihood for this process. It's not a chi-square likelihood, it's something else. The nice thing of this is that we can also write it in the time domain. And the reason this is important is that we can actually overcome all the problems and the hurdles that are due to the window function of work in a time domain. And we can also treat accurately the cases of unevenly spaced time series. On the right-hand plot, you can see an example, simulated example, which the red plot is just the expectancy value of our process. So this is the model from which the data is generated. The blue line is just a simulated light curve, again, simulated from the red line. And then if you maximize our likelihood function, you get the yellow line, which is basically recover very well both the power spectrum and the periodicity in the Fourier space, which is translated to a time delay in the real space. So there is a hope that we can actually use ULTRASAT-like data to both look for lens quasars, measure the time delay, and also do reverberation mapping with a single band from ULTRASAT. Thank you very much.
So I think we're now through the overtime and almost to penalty kicks here. But I wanted to say a huge thank you to everyone who stuck it out to the end, especially for our colleagues in Israel, for whom it is now rather late in the day. And if there are questions for the science speakers, I will hang around. But also, if there are questions about programmatic stuff, shoot me an email or shoot me and Valerie an email. Technical questions, you can ask me or you can ask Yossi. And now I'll just pause and ask if anyone has questions for the science talks. All right. Well, for those in the room, if anyone wants to gather for some kind of lunch after this, you know, I'm open. And just huge thanks to everyone who has made this happen.
Thank you, James, for organizing this and initiating this. And I hope that many will apply to join the ULTRASAT working groups.
Thanks, Ellie. Okay, I'm going to stop the recording.